A cosmic clock is counting down right above our heads, and when it hits zero, the night sky will change forever. Just 650 light years away, a sleeping giant holds our galaxy hostage. Its name is Betelgeuse. This star is a volatile, aging supergiant, and its final act will be a supernova, a detonation of unimaginable power that will rip through space. But what will that cataclysm look like from our backyard? And when will the final moment arrive? I'm Alex, and welcome to Wines of Thought. Today, we're unraveling the complete story of Betelgeuse, including startling new research that reveals why this star is acting so erratically, and what its strange behavior tells us about its final days. Let's start with the fundamentals. Betelgeuse is the 10th brightest star we can see, forming the left shoulder in the constellation Orion. If you gaze up, you'll notice its distinct reddish hue and its pronounced, shimmering twinkle. This color is a classic signature of its type. Betelgeuse is a red supergiant, a stellar category far larger than our own Sun. Its radius is so vast it would extend past the orbit of Mars. To put it in perspective, this star is nearly 900 times wider than our Sun, yet it may only be about 10 times more massive. This means its density is incredibly low. Its gravitational hold is so weak that material constantly threatens to drift away, which is why we observe massive convection cells, like boiling bubbles, on its surface in simulations. Imagine watching a sunset from a world orbiting this turbulent star. But the burning question, the reason we're all here, is about its death. Supernovae within our own Milky Way are rare events. While astronomers spot hundreds of these explosions in distant galaxies every year, that's mostly because there are so many galaxies. In our own cosmic neighborhood, we only witness 2 or 3 per century. So the chances of one happening tomorrow are slim, but not zero. What would be the consequences of such a blast? The answer, of course, depends entirely on distance. Evidence from archaeological digs suggests Earth has felt the shock waves of supernovae before. Our planet exists inside a region known as the local bubble, a sparse area of interstellar space about 1,000 light-years across. Scientists believe this cavity was carved out by a supernova blast that occurred 10 to 20 million years ago, an event our world would have experienced. I've explored that in another video, which you can find here. Researchers have also found clues of another explosion 2.5 million years in the past, detected through high levels of specific isotopes like iron-60 in the geological record. That one was far enough to be safe. Some experts even theorize that a piece of supernova debris might have struck Earth around 13,000 years ago, potentially contributing to the extinction of creatures like the woolly mammoth. The suspected impact site contains magnetic spherules and radioactive potassium-40, materials often found in the debris cloud of a star explosion, a telling clue from the era when mammoths vanished. Even older mammoth tusks from 34,000 years ago bear tiny pits from grains of iron traveling at incredible speeds, up to 10,000 kilometers per second. That velocity matches the expected speed of matter ejected from a supernova. It couldn't have been pleasant for those ancient animals. This dive into Earth's deep past reveals a critical insight. If life has persisted for 3.7 billion years, and we've endured several nearby supernovae in the last 20 million years, then these events can't be universally destructive. So, what's the real danger threshold? It all comes down to proximity. A nuclear detonation 1,000 kilometers away is one thing. One on your doorstep is entirely another. And in the cosmic scheme, our solar system could be on someone's doorstep. To grasp the sheer power of these explosions, we need to understand how they occur. There are two primary paths a star can take to reach its explosive end, but it must be the right kind of star. The first path leads to a Type Ia supernova. This usually involves a white dwarf star in a binary pair slowly stealing matter from its companion. The process isn't fully understood, but we know the white dwarf. A dense stellar remnant with a core of carbon, like a massive cosmic diamond, exists in a fragile balance. Two mighty forces oppose each other, the outward pressure of electrons and the inward crush of gravity. This means atoms inherently resist being compressed too tightly. Their electrons maintain specific orbits and will fight being pushed closer. But gravity is relentless, especially in an object as dense as a white dwarf, where a piece the size of a sugar cube can weigh as much as a car. In a binary system where the white dwarf is constantly feeding, gravity eventually wins. It overcomes the electron pressure, and the entire structure collapses in an instant. Carbon fusion ignites across the star. In mere seconds, most of its mass undergoes fusion, creating heavier elements and unleashing an unbelievable wave of energy as the star rearranges itself into a more stable state. How much energy are we talking about? Roughly 1 quattuordecillion joules. That's a 1 followed by 45 zeros. If you say you were familiar with that number beforehand, you're probably not being entirely truthful. This colossal energy is released in a flash, ejecting the star's entire contents outward at speeds approaching 6% of light speed. It floods the galaxy with gamma radiation. The event shines with a brilliance 5 billion times that of our Sun, visible for weeks until the expanding debris cloud begins to fade. The second type, a Type 22 supernova, follows a similar destructive principle, but involves a different kind of star. This is the category that matters for Betelgeuse. It requires a massive star, at least 5 times heavier than the Sun, that has reached the end of its life. These stars are still actively burning, and their balance is maintained not just by electron pressure, but also by the intense heat from fusion, turning hydrogen into helium in their cores. We are living in the shadow of a stellar time. The fate of Betelgeuse is sealed by these same unyielding physical laws. Its core is a furnace running out of fuel, and its final, violent rebirth will be a spectacle for the ages. As we piece together the clues from its recent dimming and brightening episodes, a clearer picture is emerging. The star isn't just dying, it's in its death throes. The question is no longer if it will explode, but when. And when it does, it will write its final chapter across our sky. The end of a star is the beginning of new worlds. If this journey through the life and impending death of a cosmic giant fascinated you, please support our channel. Give this video a like and subscribe to Wines of Thought for more deep dives into the galaxy stream. There's a hidden secret about Betelgeuse that scientists just uncovered, and it changes everything we thought we knew about this dying star. This fusion process creates tremendous internal pressure that fights against gravity's relentless pull to crush the star inward. But eventually, the hydrogen fuel in the core depletes, converted entirely to helium. When fusion halts, the core can no longer resist gravity's compression. The core collapses, but if the star has sufficient mass, this compression ignites fusion once more, this time burning helium into heavier elements like carbon, then oxygen and neon. With each new fusion cycle, the star's internal pressure forces its diameter to expand until it enters the red supergiant phase, with its core transforming predominantly into iron. Just like with the Type Ia supernova, the balance eventually shatters. This time, the star simply runs out of usable fuel. Red supergiants cannot fuse elements beyond iron, so the fusion process stops completely. Without this energy pushing outward, electron degeneracy pressure alone cannot support the star's immense weight, creating a collapse scenario similar to what we saw with Type Ia. The key difference is that while part of a massive star remains,
often collapsing into a neutron star or black hole. White dwarfs typically vanish entirely. But what would this cosmic detonation mean for our world? Could it actually destroy Earth? The sheer scale of material and energy released in a supernova is staggering. Anything positioned immediately adjacent to it wouldn't stand a chance. This is energy powerful enough to tear apart an entire star. A planet in the immediate vicinity would be utterly defenseless. Our Sun, fortunately, will never go supernova since it lacks sufficient mass. But if it did, Earth would likely be partially or completely vaporized. Its rocky surface reaching boiling temperatures 15 times hotter than our Sun's surface, stripped away during the weeks of the supernova's passing. What's surprising is how rapidly this initial wave of destruction diminishes with distance. In reality, vaporization isn't even the greatest threat a supernova presents. Back in 2011, researchers at the University of Cambridge calculated that planets orbiting as close as 15 billion kilometers, about 100 times the Earth-Sun distance, would remain physically intact, though they'd be sent flying through space with nothing left to orbit. Of course, any hypothetical ecosystem on such a world would face different challenges. Temperatures would plunge dramatically, creating an instant deep freeze. Even if a planet's crust remained undisturbed, that doesn't mean life could survive. The light from a supernova can outshine an entire galaxy, potentially causing blindness for any observers. Simply losing our atmosphere would create catastrophic problems. Intense radiation levels, even if not directly harming us, would chemically alter our atmosphere, destroying the ozone layer, dramatically increasing radiation poisoning risks, and killing ocean phytoplankton, triggering mass extinctions as effects cascaded up the food chain. Scientists estimate this lethal zone extends about 25 light years. Beyond that distance, the supernova's fury diminishes as it spreads across space. The asteroid impacts that potentially affected mammoths came from a supernova approximately 250 light years away. If that theory holds, then we're likely unfortunate chance events. Generally, we wouldn't detect any damage from a supernova at that range. Radiation levels wouldn't be high enough to cause mass extinctions. At 500 light years, we'd barely notice the event except for seeing an exceptionally bright new star in the sky. So you can breathe easily. Betelgeuse poses no immediate threat. But are there other supernova candidates within 300 light years that we should worry about? Fortunately, scientists are reasonably confident the answer is no. The massive stars are quite noticeable and the only two at risk of imminent supernova. Betelgeuse and Antares. Both sit over 400 light years away. White dwarfs present a trickier challenge because of their faintness. They've traditionally been difficult to detect, making risk assessment harder. However, in 2013, the European Space Agency's Gaia Space Observatory released a massive data trove from its stellar mapping mission, allowing scientists to identify 13,000 white dwarf stars within 326 light years of us. Thankfully, despite this large number, researchers remain confident none are scheduled to explode soon. With soon meaning within the next several 100,000 years. So we're safe from supernovae for the foreseeable future. When Betelgeuse finally explodes, it likely won't threaten Earth. The shockwave traveling from Betelgeuse would take considerable time to reach us, and even upon arrival, it would carry less force than our solar wind. It wouldn't be our magnetosphere or atmosphere providing protection. The Sun's heliosphere alone would be sufficient to shield us from such a distant supernova. How much time remains before the grand finale? No harm will come to Earth, but the spectacle will be breathtaking, potentially shining as bright as a full moon. visible even in daylight. Just imagine that. Witnessing a supernova glowing in our sky would be a phenomenal sight, and it could also reveal many secrets about the mysterious process of stellar explosions. So there's tremendous scientific interest in Betelgeuse, much are focused on that single burning question. When will it detonate? Betelgeuse will explode soon, though I use that term in an astronomical timescale. This means it could take up to 100,000. However, some researchers predict this red supergiant might detonate within the coming decades. Their work operates on the assumption that Betelgeuse has a significantly larger radius than previously thought, and if correct, we might witness a local supernova within our lifetimes. But Betelgeuse doesn't surrender its secrets easily. Over recent decades, it has consistently surprised us. The inner workings of stars are complex, and Betelgeuse dims and brightens according to several incompletely understood cycles. It has a fundamental rhythm probably connected to its eventual detonation, plus several overtones. Separate but related patterns. These cycles can range from a few hundred days up to 2,170 days, and there's ongoing debate about which cycle represents the fundamental one versus the overtones. Since these patterns aren't fully decoded, Betelgeuse always seems to be doing something interesting. It made headlines in 2009 when it contracted by 15%. You all might recall the Great Dimming of 2019, when scientists initially couldn't explain the phenomenon. Speculation surged that this might be a precursor to the long-awaited supernova, though unfortunately that probably wasn't the case. New data from the Hubble Space Telescope suggested the star itself wasn't actually dimming, but rather that some dust ejected by the star had cooled and obscured our view. In September 2019, Hubble observed heated material moving away from the star's atmosphere. Over subsequent months, this material was tracked near the star. By December, the star's southern hemisphere began dimming. The theory suggests heated carbon was in this outflow, and as it moved around the star, it expanded and cooled. When we lost visual contact, it wasn't because the material moved away, but because it passed directly across our line of sight to Betelgeuse. At its dimmest, Betelgeuse was 2/3 less bright than normal. However, since April 2020, Betelgeuse has returned to its usual brightness, meaning this dust cloud has either moved aside or dispersed completely. This event, however, sparked renewed scientific interest in Betelgeuse and led to an astonishing discovery. Betelgeuse regularly brightens and dims in various cycles, but not all these fluctuations are likely caused by dust ejection. At least one cycle might instead be the work of a small companion. For over a century, scientists have wondered if Betelgeuse might actually be part of a binary system, with a tiny sibling star caught in its gravitational embrace. Proving this was enormously challenging because Betelgeuse's surface is so unstable and variable that tracking the dimming and brightening indicating such a star's passage seemed nearly impossible. The universe always keeps its most fascinating secrets just beyond our immediate reach. However, after the Great Dimming of 2019, many more researchers turned their attention to Betelgeuse, and two independent teams found evidence that the longer cycle, the one repeating every 2,170 days, could only be explained by Betelgeuse having a neighbor. The key to proving the existence of Betelgeuse's buddy, colloquially called Betelbuddy, though officially named Suwarha, lay in examining historical radial velocity and positioning data. Sometimes the biggest discoveries come from questioning what we thought we already knew. A groundbreaking discovery about Betelgeuse has just emerged, revealing a hidden companion that explains its bizarre behavior. Research teams from the Harvard-Smithsonian Center for Astrophysics and the Flatiron Institute's Computational Astrophysics Center independently analyzed Betelgeuse's motion
detecting a subtle repeating wobble in its position. This oscillation is as if the star were being gently tugged from side to side, aligned perfectly with periods of dimming strongly indicating the gravitational influence of an orbiting partner. Both groups estimate this companion, nicknamed Betelbuddy, has a mass similar to our Sun and orbits at a distance roughly equivalent to between our Sun and Saturn. Equipped with these findings, other astronomers joined the investigation. Initial attempts using space telescopes failed to detect the elusive star, so researchers turned to the Gemini North Telescope in Hawaii. They aimed its powerful 8.1-meter mirror toward Betelgeuse, employing a high-resolution speckle imager that captures thousands of brief exposures to counteract atmospheric distortion. They timed their observation for when the predicted companion was at its maximum separation from the giant star. And there it was, faint, blurred speck believed to be Sawarha, the official name for Betelbuddy. Its light is dramatically dimmer, about 6 magnitudes fainter than its brilliant host. This image pushes the absolute limits of Gemini's resolving power. While not definitive proof, the detection aligns with numerous other observations and predictions, making it highly probable this is the long-sought companion. Final confirmation may require waiting until 2027, when it next reaches its greatest apparent distance from Betelgeuse. If verified, this adds a captivating chapter to the star's narrative. It also allows astronomers to dismiss the longer cycle as the fundamental mode, the primary rhythm that determines Betelgeuse's supernova timetable. Regrettably, this makes it more likely the explosion will not occur for a much longer time, possibly beyond our lifetimes. While disappointing for us, it's likely a reprieve for Betelbuddy itself, which will be squarely inside the destruction zone when Betelgeuse finally erupts. The cosmos conceals its most profound truths in plain sight. The problem with Betelgeuse's spin, predicting the moment of detonation, remains incredibly challenging, partly because Betelgeuse continues to baffle us with its actions. For instance, data from the ALMA telescope network indicates Betelgeuse is rotating at an astonishing rate, completing one full turn approximately every 2 decades. That might sound slow, but for a star of its immense size, this means its surface is whirling at about 18,000 kilometers per hour, or roughly 5 kilometers every second. It's 10 times faster than the rotational velocity we experience on Earth's surface, and for a supergiant star, it seemingly violates established physics. How can we determine this? Let's begin with the fundamentals. Measuring celestial rotation employs several methods. For large nearby objects like the Sun, Moon, or planets, we can simply observe features moving through a telescope. The Moon's angular diameter is about half a degree, and you can see its details with the naked eye. Jupiter's angular size is 1/100th of a degree, yet its characteristics are clear through optics. But what about Betelgeuse, the colossal star 650 light-years away? Despite its enormity, its vast distance means its angular diameter is 1,000 times smaller than Jupiter's, rendering it a distinct smudge, even through our most advanced instruments. So how do we gauge the spin of something we can't clearly see? Fortunately, an alternative technique exists, relying on a principle you may already know: the Doppler effect. This is the same phenomenon that alters the pitch of a siren as an ambulance drives past. When it approaches, the sound waves compress, raising the pitch. As it recedes, the waves stretch, lowering the pitch. This effect also applies to light waves. When a light source moves toward yellow, its light shifts slightly toward the blue end of the spectrum. When it moves away, it shifts toward red.
We don't notice this with everyday objects because light speed is so immense, requiring much higher velocities for the shift to be detectable. Now, back to Betelgeuse. When a star rotates, one hemisphere moves toward Earth while the opposite hemisphere moves away. This creates a color gradient across the star's surface that telescopes can detect, even if the star itself appears blurry. By identifying which side is blue shifted and which is red shifted, we can deduce the rotation direction. The degree of color difference allows calculation of the rotational speed. This is precisely how astronomers used ALMA data to determine Betelgeuse's surface spins at 5 kilometers per second. This seems straightforward, but established stellar physics asserts that 5 kilometers/s is an impossibly fast for a red supergiant like Betelgeuse. Consider our Sun. It rotates at about 2 kilometers/s, but it's 1,000 times smaller and roughly 10 times less massive than Betelgeuse. If our Sun expanded to Betelgeuse's size, swallowing the inner solar system and nearly reaching Jupiter, its rotational velocity would plummet to a mere 2 meters per second to conserve angular momentum, much like an ice skater slows when extending their arms. If it also gained mass to match Betelgeuse, the speed would drop to 0.2 meters per second. So, bigger and heavier stars should spin slower. Yet Betelgeuse defiantly contradicts this. What is causing this anomaly? Cannibal stars. One hypothesis is that Betelgeuse acquired this excess angular momentum through stellar cannibalism. This process occurs when one star consumes its binary companion. The predator star's gravity gradually strips away the companion's gaseous layers until only its core remains. This accreted gas carries significant angular momentum, causing the consuming star to both expand and rotate faster than normally possible. But is this truly what happened to Betelgeuse, or is a deeper mystery at play? A collaborative team from Europe and China has proposed that Betelgeuse's outrageous rotation might be a massive illusion. To understand how, recall what ALMA actually measured. Despite blurry images, they discerned that one half of Betelgeuse emitted slightly redder light, while the other half emitted slightly bluer light. The straightforward interpretation is stellar rotation, with one side approaching us and the other receding. A green arrow in Betelgeuse imagery often symbolizes this proposed spin axis. But could another mechanism produce this color split? Simulations show Betelgeuse's surface is a violently turbulent cauldron, constantly seething with immense heat like a boiling pot. These convecting gas bubbles are colossal, some spanning 100 million kilometers, covering significant portions of the star. They surge outward at terrifying speeds up to 30 kilometers/s. If one such bubble were headed toward you, no spacecraft could outrun it. Your only hope would be for it to collapse back onto the surface before impact. In the chaos of the star's death, we find the seeds of new understanding. As these gigantic bubbles rise and fall across Betelgeuse, the surface becomes a patchwork of regions, either moving toward or away from Earth. Consequently, Doppler shifting causes light from these areas to be blue shifted or red shifted. This turbulent mosaic could create the observed color gradient, mimicking the signature of rapid rotation without the star actually spinning that fast. The enigma of Betelgeuse continues to challenge and fascinate, reminding us that the universe always has more secrets to reveal. If unraveling cosmic mysteries with us sparks your curiosity, please support our channel. Give this video a like and subscribe to Lines of Thought for more journeys into the heart of space's galaxy stream. A startling new revelation suggests we may have been completely mistaken about Betelgeuse's rapid spin. An international collaboration of scientists has released a paper contesting all prior interpretations of the star's rotation. They propose that Betelgeuse might not be spinning quickly at all. Instead, the ALMA telescope data could be registering a spectrum of light frequencies resulting from violent surface chaos. Consequently, researchers might have erroneously attributed these frequency changes to rotational effects. But for those deeply familiar with astrophysics, a significant question remains unanswered.
A genuinely rotating star would generate a seamless progression of light frequencies, shifting from blue-shifted hues on one limb to red-shifted tones on the other. On the flip side, a star dominated by turbulence would exhibit a disordered assortment of colors, with blue zones marking ascending gas and red areas indicating descending material. How could the ALMA team have possibly confused these distinct phenomena? If observations revealed a smooth color transition, shouldn't the turbulent model be immediately dismissed? In a perfect scenario, that logic would hold. Smooth gradients imply rotation, while scattered patches indicate bubbling activity. However, we must recall that Betelgeuse lies at such an immense distance that the images captured by ALMA are far from crystal clear. They're more akin to a blurred snapshot than a high-definition portrait. When scientists run simulations that incorporate the constrained resolution of our instruments, they forecast that these bubbling regions of redshift and blueshift will be misinterpreted as a rotational gradient nearly 90% of the time. This implies that even if the ALMA astronomers conducted flawless analysis, they could have been tricked by Betelgeuse's seething surface into believing it rotates much faster than reality. This also signifies that researchers are now pursuing a crucial goal: higher resolution examinations of Betelgeuse that can more precisely distinguish between these two possibilities.
The encouraging update is that superior images of Betelgeuse have already been acquired using the same telescope, but with extended exposure durations. The disappointing aspect for those eager for answers is that it will probably require several years before these images are thoroughly examined. Those solutions are on their way, however. Currently, I'm intrigued to learn where you wager your confidence. Is Betelgeuse truly revolving at 5 kilometers per second after devouring its partner star? Or will the fresh assertion that this rotational velocity is merely a visual deception be confirmed? The greatest cosmic mysteries often lie in what we think we see. So here we are. All you could need to understand about Betelgeuse, a star poised on the edge of disaster. It's hardly surprising that we regard such a violent occurrence with such intense curiosity. Humanity adores explosions, as evidenced by every society's affection for celebratory pyrotechnics. Thus, whenever it occurs, a supernova eruption that illuminates the heavens would be a magnificent spectacle to witness. Although I'm relieved that, with Betelgeuse, we'll observe it from a perfectly secure vantage. In the stellar dance of death, we find life's most profound lessons. If exploring the enigmas of the cosmos with us has ignited your imagination, please help our mission. Give this video a like and subscribe to Remains of Thought for more voyages to the frontiers of knowledge. Thank you for watching.